Hello everyone, myself Girish with SolidWorks tutorials. In this session, we'll just go ahead with the part 2 of this SolidWorks flow simulation, wherein I'm gonna cover the uh, multi-stage and single-stage centrifugal pumps, how they're gonna work with respect to the rotating regions. So how to define the rotating regions, so how to deal with the pressure drops, and how to get the uh, velocity of lots and all. Yeah, so as we have discussed, the multi-stage centrifugal pump. So it has two stages. So I'll activate the section view for the same. Okay, so here you could see. So this is how it is customized. So inside these are the impellers. Okay, and then these are the state locations where the uh, involute will be there. Due to that, the pressure will be created. Okay, well, we'll see the working principle of it. So as you could see, how the impeller will rotate with respect to the shaft rotation. So the shaft will provide the power to just rotate this impellers as well as the other rotating regions, so that the suction will be created to produce more total head required to just pressurize the water to lift the water as well. Okay, so inside we need to create the rotating regions to deal with this kind of flow analysis. So here we are considering the entire model into account, that is internal flow analysis, and we're gonna define the rotating regions to calculate the same. Okay, so we'll just switch to the flow simulation and I'll explain you the scenario which and all we have taken into account and what and all you need to do to deal with the same. The project one which I have created, so here I'll explain the general settings. The first thing is you need to set the unit system as we do, right? So once you're done with this, the analysis type you need to define. So here I have taken the internal analysis into account as the flow is flowing inside the entire casing, and I'm going to exclude the cavities which doesn't have the flow conditions, and then the rotation region should be activated. This is the very important criteria here while dealing with the rotating regions. Okay, so if you are using 2019 SP0 version, there is a bug, so you can't activate this rotating region, that is rotation. So you need to upgrade your service pack to get this update, remember that. Okay, so the fluid region, water have taken into account, and the flow type is by default turbulent. If you want to change it to laminar, you can do it. Wall conditions, okay, cavitation, so we have explained about the cavitations in the previous session, basics, right? So if you want to see the effect of cavitation, you can simply check this. Right now I'll just keep it apart. The wall conditions, I'll take adiabatic. There is no any viscosity effects and all in this, so if it is there, I'm gonna neglect it. And the final initial conditions I'll keep as default, no more changes. Temperature is default and the pressure is same. Okay, so once you're done with this, you can directly go ahead with the boundary conditions and the fluid computational domain. Okay, you could see this is the by default fluid domain which has been created by just checking up the inlet and outlet fluids. So according to that, the fluid domain is created. So if you want to again customize it, you can do it. For now it's okay, no need to change. Well, so I have defined the inlet lid here, okay, and the outlet lid at that side. This is where I have defined the same thing. And next thing is to deal with the rotating region. So you need to define the rotating region design. So you cannot directly rotate these impellers, you need to consider the regions. So you need to create a region like this, as you could see. Okay, you need to create a separate CAD model to cover this region, so which region you want to rotate. Okay, and this region you need to rotate it with respect to the rotating region by just selecting this cat part into account. Okay, so whatever is covered inside the portion will be rotated by just selecting these two. Okay, rotating cat models. So I have previously defined it, you don't need to worry about it. The angle I have defined is minus 1000 radians per second anti-clockwise, minus sign. Okay, so once you define these, you can directly go ahead with the boundary conditions. So I'm not going to define any of the inlet volume or velocity flow or whatever it is. I'm just going to define the environmental pressure. Both the locations same thing, and due to this impeller rotation, the inside suction will be created, and due to that the water will be pulled outside. Okay, yep. So after this you can define the goals which and all you are looking for. Let's say my main concern is to deal with the pressure drop. Okay, and the global goals like static pressure and the total pressure and the average velocities, that is global average velocity. So my concern is to deal with the global velocity along y direction. So inlet pressure and outlet pressure, here you could see I have considered total maximum pressure into account for the both. I have selected the surface goal for these things, take a note of it. So once you define these two surface goals for inlet and outlet pressures, you can use the formula by defining the equation goals. You can add equation like outlet minus inlet, which is equal to pressure drop. Okay, so once you are done with this, you can mesh it. So I have taken the very fine mesh, so automated mesh it is. So if you want to refine it with respect to the advanced options, you can do it, but it's gonna take more time for me, so I'll just consider the by default automated level 7 mesh. So once you're done with these all the steps, you can simply run this analysis. So depending upon your system configuration, it's gonna take 5 to 10 minutes or more than that if you're using 2 GB RAM or something. Okay, as you could see, while just running this, you can activate these slots. So you can see the velocities keeps on fluctuating in the range of 8 to 12. I'll activate the cut float here. This is the velocity float. So here you could see the maximum velocity is 25.157 meter per second. So I'll simply choose the display state to just show the result. So here you could see how the velocity distribution is taking place. Due to the rotation of the impellers, the velocity is more at the impeller regions, and then it keeps on decreasing. Okay, and once it goes through the outlet, the velocity will be approximately near to 10, 7 or 8. And if you want to animate this, you could animate it. As you could see, at exactly the impeller center region, the fluid velocity is very high, that is 25 meter per second. And I'll activate the pressure float. So you can hide the velocity float. Okay, here you could see this is how the pressure distribution takes place inside the model. So this is about the cut floats. So if you are going to deal with the flow trajectories, you can activate, and here I have selected the inlet into account, and due to that I have created the float with pipes, not the arrows. Okay, so this is how the rotation of fluid gonna takes place at the impeller, and then the flow will be forced towards outlet, and this is how the rotation of the fluid also takes place inside, you could see, right? Yeah, so this is about the flow trajectories. Now to deal with the goals, you can use the goals plot. Okay, So I have selected only the average velocity along y direction and the pressure drop. So you can simply show that too, and you could see the average velocity, global velocity is maximum 10 and the average is 9, minimum is 7. So we can consider from 7.6 to 10.6 will be our flow in the form of meter per second. You can even convert in the form of LPM and all. So even you can consider gallons if you're dealing with the different standards. So the pressure drop, you could see the average and maximum and the minimum values. So if you want to calculate the total height, you can even consider these. And you can even see the history plots, see how the velocity and the pressure drop is fluctuating. Okay, so even you can just refine your model by just changing the impeller design as well as the impeller speed and all to obtain the better results. So this is a simple scenario which I have explained. I haven't considered any of the technical documentation or any of the uh, practical testing which has been done. So this is a basics how you can simply define the rotating regions and the practical conditions into account, and you can run the analysis. Okay. Yep. So that's all about this particular rotating regions, multi-stage submersible pumps into account. So in the later stages, we'll just deal with the single stage centrifugal pump to just deal with the same. Here if you want to see the impeller design, you could see here, and this is the curved blade impeller. So we have even seen the velocity distributions on it, right, the chart. So you can make the modifications to get the better flow inside the submersible pumps. Okay, that's all about this. Now we'll see the single stage centrifugal pump. Okay, how exactly we need to deal with this particular scenario. As you could see, here is also a single impeller and the inlet and outlet we have defined. This side the shaft will be there and the motor will be implemented, so that part is not needed here. So I'll just skip that part. Okay, so let me just hide the components. So this is the impeller, rotating impeller, and we have the rotating region here. So if you're going to deal with this kind of analysis where the rotating regions are included, you need to create the rotating regions according to the rotating impeller size. So that entire rotating impeller should be covered inside that rotating region. So just to showcase that one, so I'll open it for you so that you could understand how to create the rotating regions. Okay, so let me just open it. Yeah, so this is the region. So by using the revolve feature, I could able to do it, and this is the sketch. Okay, simply you just need to revolve according to the size of the rotating impeller which you have it. Okay, so once you are done with that, you can directly go ahead with the defining the boundary conditions by using the wizard. So I'll just showcase the same. Yeah, so first thing you need to define the init systems by using wizard, and then the analysis type. So we are considering the internal flow analysis, and the rotation region should be activated as I explained before. The fluid medium is water anyway, and even you can consider the petroleum crude oils as well. So if you are going to deal with that particular industry, cavitation is required. If required, you can activate, or else you can keep it blank. Wall adiabatic, no viscosity effects. If it is there, it is quite negligible for this analysis here. Other initial conditions by default, whatever it is that I'll take into account. Well, once it is done, so you can just define the rotating region. The computational fluid domain will be automatically created, and if you want to customize it, you can go ahead with that. Here you could see I have considered the region which I have created, and that should rotate with respect to 200 radians per second. Okay, so as this what particular single stage motor can produce approximately nearly 200 radians per second rotations. So you can define the same, or if you have any study data, you can just take into same. This inlet velocity not required actually, because I'm just gonna consider the impel rotation into account. So according to that, how the fluid flow will be there into account. So that I need to consider. So the environmental pressure for the outlet I have defined. So I'll simply delete this one. It is not needed. Okay. Yeah. So after this, I'm going to define the goals, the global goal, average velocity, and the maximum velocity. I want to cross check how much the velocity of the fluid will be gained at the output, that is globally. Here you can activate the surface goals. Okay, this is the mesh, the quite fine mesh I have used, level 7. So if you want to customize it according to the advanced boundary conditions, you can go ahead with the one more session is there, that you can just refer it how to deal with that particular meshing. So that would take much time, so I have considered the simple meshing. So after this, I'm gonna run the study, so you could see how exactly the flow is taking place. So these are the multiple iterations. Okay, so once this is done, you can accept the floats. So this is the cut float. You could see this is the velocity float. The maximum velocity could see it is 30 meter per second approx, right? Yeah, so even you can change the floats by using the simple float drop down option here only. Instead of creating new, I'll just switch to the pressure float, green check, and this is how the pressure will be generated. The stator and the rotating regions will help us to just gain this kind of the extra uh, potential energy by creating the high pressure into account to create the total head required. Okay, yeah, so I'll activate the flow trajectory so that we can understand how exactly the fluid flow is happening inside. Okay, so I'll hide this plot. Yep, you could see how exactly the fluid is surrounding the impeller and how it is just coming out from the veins, the volute and the inlet. You could see the velocity at the outlet region. This is quite more fine. So this is how you can just carry out the flow simulation by using SolidWorks flow simulation for the rotational regions for multi-stage as well as for single stage. Okay, these are the goals here. I have defined two goals, that is the average and maximum velocity. Could see the average velocity is approximately 11 and the maximum velocity is 30 meter per second. Okay, so yep, that's all about this one. To summarize this session, so we have gone through the multi-stage and single stage rotating regions, and we had carried out the pressure drop analysis and velocity distributions and the outlet velocities as well. Yep, that's all about the session. Please do like, comment and share the uh, tutorials. Once again, thank you all. Stay tuned.